Okay, we'll continue this lesson about k-nearest neighbor. Last time we stopped at this feature scaling, right? Using normalization or standardization to put the different different feature on the same scale, so they have the same influence when you calculate the Euclidean distance. I think the feature engineering for this case, it's ready. So now next we can build the model. It's exactly the same as what we did. You just import the library and then get to the library, get this function, right? Get this function, and then you use this function to fit the x and y, and then you can use this model to predict. So, but however, here there are some arguments you want to pay attention to. This is the n neighbor equals 1, which means that only based on one neighbor. Okay, and if you want to n based on 2 neighbor or 3 neighbor, then this number should be changed. And this matrix means that this will choose the Minkowski. This matrix, if we choose this matrix and choose this power equals 2, that means you're using Euclidean distance. I believe the default value is 2. Default value should be 2. That is a Euclidean distance. Let's quickly check, okay? See, this power default value is 2. So if power equals 1, that means you get the x plus. So if power what is now working? Yeah. It doesn't work. All right. If power equals 1, that means we use a Manhattan distance. But usually you just this one is the most commonly used. Okay. So next, we are going to use this model to predict the predict the classes for all the points on this coordinates. So the purpose of this step is to demonstrate how this model fit for this data set. Okay. Actually, it is to demonstrate that when k equals 1, how this algorithm works. Right? So here, this part is not required in your assignments, so you can just quickly have a quick view of this code, but it's fine. You don't have to understand completely. This x and the x2 is just a 2 variable. This is the x1 variable, and this represents the x2 variable, and then the color, this z represents the y value, the target value, whether the outcome is 0 or 1 or 2. there were 3 classes in this data set, right? Still hope this will work. Does anybody know? Yeah, why this is not working this way? So I'll just copy this code quickly. And here we built like a map of this contour of this coordinate on this coordinate, and it's based on the x1 is the sepal width and x2 is the pedal length, and then the colors will be the colors of this map will be based on the y value. Okay. So this is the result we get after using the classifier k equals 1. If we observe this, what do you think? Observe this. What do you think of this model? Is a good model or not? Do you think it's a good model or not that accurate? Quite been very accurate. It's actually too accurate. For example, here, these dots, it will be predicted as blue. All this area blue looks fine, but this area, it should be a whole yellow area, right? A whole yellow area for this class. However, if your xy value and no x1 x2 value is here, then this will be predicted as gray. However, if we all can easily see that it should be in the yellow area, right? But because of these outlier here, the values here will be predicted wrong. So if you have k equals 1, this is only based on one neighbor, then this model is very sensitive to the outlier. For example, if you have an outlier, a blue class here, then this area will also be predicted as gray, right? So this is too accurate. This is actually not a good model. What we call overfitting. It's overfitting the data, training data. And if we do k equals be like 3 here model, right? N neighbor equals v5, Let's see how it changes, how this picture changes. You can see if k equals 5, it is the same. It's the same. It was the same.
Yeah, same dots.
Same dots, right? It is the same dots. Yes, it's the same dots, but it classifies it much better. You see, this whole area is yellow, and this whole area is gray, and it's not influenced by the outline that much. And yeah, if k equals 10, it will be even better, even smoother. This border line will be even smoother. So k equals 1 usually leads to overfitting, or k equals 2. Those are not good values. When you choose k, it should not exceed the number of rows for training. Usually the optimal k is found at the square root of n, like the number of n represents the number of cases, but usually I don't go over like k equals 20, okay, or else that's just the computation. It costs too much computation. And we mentioned that this already, k should not be an odd number if if it has 2 classes, and the k should not be the multiple of the number of classes. Okay, next, this one we built upon all the data set, but usually we split the data set into training and testing. Training, testing, and then they use the testing data to predict, to verify the model, right? So let's do this one. Okay, we get an accuracy of 0.33, 0.833. That's pretty good. So one problem we have to be aware of, this random state. If we change the random state, what will happen? What happens? Well, the data changes. Yeah, they pull out different data, right? If the random state is fixed, then it always pull out the same data, but the random state change, it will pull out the different data, and then consequently it will, because you have used different data, the accuracy will change slightly also. So for example, if I change to 100, wow, this is a 0.07 difference. That's that's a totally different, right, level. So here we introduce another technique called cross validation. What it means is, so when this random state change, this accuracy change, what we want to do is maybe like pull up, give it 10 random states, and then you get the mean value of the result. Okay, then this one better represents the actual result, right? Because it changes a lot when your random state change. But when we have like a 10 random state, you give it a 10 random state, or go over 100 examples. Okay, then this mean is quite representative of the actual result. So that's the concept behind the cross-validation. Because what you could do is, okay, you can write a for loop, and then I want to this random, you can give the program a random number, 100 different random number, and then take the mean value. Of course, you can quickly write this program as well. Here we could use this cross validation. Okay, so what this means is it runs several folds. If you set up a folds equals 5, folds equals 5, then it pull up data. Run the experiment 5 times. 5 times. Each time it pull up the different set for the testing. One question.
So in our own project, we would really be using random state as much as we're printing or we're obtaining our data through a data set and import a CSV file. We would really need the random. It's not going to use random data or.
You should use training testing split, or you could use this cross validation. Either way is fine. Yes, so yeah, I would suggest you use cross validation. Usually, this is a more common practice now, rather than training testing split. Okay. For each experiment, this is experiment 1. This pulls up with this. This is the whole data set, right? 100 cases. So for the first experiment, it pulls up this part for the testing data set. And then when it goes to the second experiment, okay, this pulls up this part for testing data set. So this is a more representative than just running one experiment, right? And the code for this is quite easy. You just give it so the code for it is quite easy, and you see, you just tell it the model. The model is the k nearest neighbor, and then you give it the x and y, and then you tell it how many experiments you want to run. This is a 10 experiment. I believe if it's so if it's 10, if it's equals 10 folds, that means that it will split the data into 10 blocks, and each time it take out 1 block, like 10% of the data for the testing. Okay. So let's see. Yeah, we can just do this first. See here, this model is be defined as a classifier, and then X string. So we don't need the X string XY anymore because we put the whole data set into this cross validation. I will take out 10% or 20% as a testing training. here we use the whole data set, okay, and y, and then this fold is a 10-fold, which means we will run 10 experiments, and each time it takes out 10% of the data as validation. So what this score will give us is I don't think I have imported the library. Yeah, so I need to import the library. What it gives us is a group of the scores. So it gives us 10 scores, 10 accuracy scores. You see, the least one is 0.8. It even get 100% accuracy. And usually you calculate the means. So yeah, this stays at 0.9. Or let's try to see if we run it again. For this cross validation, even if you run it again, it doesn't change much. It's based on the 10 experiment. Let's see if we do 5. Okay. See, it still stays pretty the same, right? The same. So this one is more stable than using training testing split. Okay, next, I think we need to go over the K value and to find what is the optimal K, right? So what we need to do is to write a loop. Probably let K goes from 1, actually 1 is not necessary, go from 2 to 20, and then exclude those multiples of 3 because there are 3 classes. Right? So, so we can just use this one. And then we give this K number to the classifier. So this one should be changed to I, right? The K value I. And then we go, we use this cross validation. And the next thing we need to do, nothing we need to do is to print out this K, this mean value. Okay, as you see, from k equals 2, it's actually 1. The 1. K equals 2, and then 4. This accuracy goes up, and then at some point it turns. It turns. So this 1 probably k equals 2, 4, 5, 7. K equals 7 reach the best accuracy. Right? Yeah. Alternatively, it would be better you print out both I and C. So this is 7. Yeah, 7 reach the best value. Okay, so that's how we find the best k value. Okay. In this code, I just put it into a data frame. So it has 2 columns. One is a k, and the other one is accuracy. Okay, so here I added some notes here. You could use this stratify k fold. So make sure, like in each fold, there are equal amounts of the classes, like how we use the stratify when you do the testing training spread. Do you all remember that? So if you don't stratify, what will happen is that when you pull up that 10% or 20%, this testing data could be all the same classes, and that's what we don't want to happen. We want to here to have a equal amount of classes in each testing, right? So that's called a stratified, right? So here, what we could do is to add this code, stratify k fold, right? And this number should be the same. This S should be from here. Cool. All right. So that's the stratified k fold. It's different, huh? See, in this code, the result I got is k optimal k was 5. Here, the result I got is optimal k is 7. And the change is to 10. Probably it changing. Yeah, so now this is 5. The optimal k is 5. So changes a little bit, you see. If you plot this k value, you will see line plots. At some point here, k equals 5, this accuracy goes down. So this is the best k value you could have. Next one, we want to talk about the accuracy, precision, different measuring metrics. So here, this is now a good case. So here I used another case to explain this. Here we want to predict breast cancer. Here we have 2 cases, 2 models, 2 prediction models. They give us this result. If we only use accuracy, what we can see is it would be so helpful if I can use this pen, but it's not working today. Sure. Okay. How do we calculate the accuracy? Tell me, how do you calculate the accuracy of these two models? Give me the equation of this one, model A, and then equation of model B for accuracy, for calculating its accuracy.
Like the difference between like the blue and the blue, and then like the difference between each square. Between two of them.
Accuracy is the what you predicted right, divided by all the cases. So here, which blocks are the ones for the top of the equation? It should be
Divide the
what's the number?
top number by the, like, you want each individual average for each block or?
For each box, yeah, because these two are resulted from two different models.
Mhm.
And we are using this accuracy to see which model is better.
Like 31, would you divide that by the actual?
What's the equation for this first one? Accuracy is what you predicted right, divided by what you predicted wrong plus right, actually all the cases. The percentage of the cases that you predicted correct. So it should be
Variable, well, not variable, that's whatever you want the variables to. Yeah.
yes. So this is 0, 0. So it should be 0, 0 is 31 plus which corner is also predicted correct plus y1 plus which box. This is the correct ones, right? It was 0 and it was predicted 0. What is the other box on this top? The bottom should be all the cases, so it's 31 plus 9 and plus 6, and all these 4 numbers. So the top number should be 31 plus which one here? Correct, yeah.
Yeah, 68.
68, yes, 68 is the true the breast cancer cases, and they are predicted as planned breast cancer. So this one is also the correct one. Right? These two is the correct one. Should be on the top. And then the bottom is all these 4 numbers. And if you calculate this one, it's the same. It's 34 plus 65 and then divided by. So this number add together, it's also 99. So these 2 model looks exactly the same. It look exactly the same, has the same accuracy. Are they really equally good? So here we introduce some other metric. It's called precision, recall, and F1 score. Right? Recall, it's in simple words, want to see in those truly breast cancer cases, these breast cancer cases, how many were predicted correct? Okay. And precision means for all those predicted correct, how many are true cases? So one is this line. Recall. The recall score is this line. Okay, this is the recall score. And then the precision score is this line, measures this line. How many cases were predicted correct for breast cancer? So in this problem, what is really important? So for all those people who have breast cancer, we want to find them out. We don't mind. There might be some people who doesn't have breast cancer, but they are predicted as breast cancer. That's fine. They will go to the next step, and they will probably receive. They will not receive false treatment. But for all those true cases, for those people with breast cancer, we don't want to skip any. So what we want to use is the recall score. Recall score. Give me the equation for the recall score. How do we calculate the recall score here? It's this line. Yeah. It calculates the true, the low of this line of the Y test value is true. So it's
Would it be like 6 minus 68 over 6 plus 68?
what do you 6?
6 minus 68 over 6 plus 68?
Close, but it doesn't have to be minus. It's just a 68. It's the cases that we were predicted out as breast cancer, and then this is a 66 plus 68. Okay. And this one, it's the same, so it should be 65 divided by this one. 9 plus 60. 65. So in all these 74 cases, both have 74 breast cancers. And this model predicted out 68%. And this one only detected 65%. The main thing. Yeah, we are doing this word problem here. Which model is better? This model, because they find the more cases of breast cancer. Another metric we often use is precision. Precision means in all those that were predicted one, how many are truly one? So this goes this direction, okay? Goes this direction. What is the equation for this one? The precision score is the precision score goes this direction. What will be the equation for the prediction? For the precision score. Like for all these cases that were predicted as breast cancer, how many are truly breast cancer? 68. So the equation should be
68.
divided by
Something plus 68.
it's 9. That's 9. So this one, the precision score is a 65. 71. 71. Which one is better? Hard to say. Hard to say. You have to use a calculator. But it depends on which metric you want. You hear probably breast cancer case. I don't mind. Some people, they don't have breast cancer, but they are predicted as a breast cancer. They may give false treatment, but probably there are some other next steps to verify the diagnosis. So that will be fine. And sometimes we cannot decide, maybe like one model has a higher precision and the other one has a higher recall, then we cannot decide which one is better. Then we can use the F1 score. F1 score is a measure based on precision score and the recall score. So the actual F1 score is it's not a good explanation. Okay. So the actual equation of this, the F1 score is this one, okay? So if this precision goes high, then this F1 score will also go high. And the recall score, same. So this F1 score is based on both precision and the recall score. If you cannot decide which score to use, F1 is a good one. So here you see there's another case. This is find fraudulent transactions. This accuracy score, it's very good. Accuracy score is a 97%. That's a very, very good model. But if we look at this, recall score, how it is. The recall score is a good model. For all those fraudulent transactions, how many it predicted out? Only one, yeah. There are how many fraudulent transactions actually? There are 30 transactions are fraudulent, and they only predicted out one. So it's a very bad model actually. That's why we have to look at not just the accuracy score, but the precision and the recall score as well. And yeah, for this precision, it doesn't look bad. There's only one. See, there's only one positive case, and so that's of course that's an extreme case that the data set is very imbalanced. Only has like 30 fraudulent transactions versus 970 non-fraudulent transactions. But for this case, of course, we want to look at the core score. Okay. For example, yeah, in the real time, wherever, like whenever I go to maybe like Alabama, if I shop at Alabama, I cannot use my card. Cannot use my card because it will send me a message. The bank will send me a message, and then oftentimes I forgot it. I need to verify this, and then oh, what's wrong with my card? And so that's what they do. Even if it's now fraudulent, they'd rather find it, they'd rather detect it as a fraudulent and send you a message. So that's the importance of using the different metrics, not just the accuracy. Okay. Okay. That comes to a summary of this lesson. So this algorithm is widely used because it's easy to understand, and in the classifier model, you need to provide two metrics. One is the k-value, and then the distance metrics. You actually can just use the default one, Euclidean distance. It works with multiple classes. So if you have multiple classes, do not choose that logistic regression. Okay. It's called a lazy learner, also KNN. When you build the training, when you build the training, it doesn't. When you build the model, it actually doesn't have the training period. So it actually doesn't. It doesn't produce a real model like linear regression. You produce a real model, and equation y equals ax plus b, and when your new cases come, you just use this model, right? You just use this equation to generate the new y values. But k nearest neighbor is different. So when the new cases come, it has to calculate again based on its neighbors, and then decide what is the class, what is the y target. That makes sense. And logistic regression, it's the same with it's similar to linear regression. Build a logistic that equation, and then when new cases come based on the x1, x2, calculate the value. But k nearest neighbor, it has to calculate every new cases based on its neighbors. So it's called a lazy learner. And when you have to predict a large amount of data, you can imagine this calculation is the cost for this calculation for the prediction process. The prediction process could go slow because it has to calculate every new case. So here, I don't know where I copy out this. I don't quite agree with this. I agree with this one more because the cost of predicting the k nearest neighbor is very high. Yeah, it doesn't build a model. Instead, it has to calculate the new case. And you should not use it when you work with a big number of features, like hundreds of features or parameters. And also because it's based on the distance, hard to work with. If your data set has all categorical features, it's hard to use this algorithm. And I believe we discussed this at the beginning of the class. Because if it has both has all categorical features, the distance you want to pull out when you want to see three neighbors. For example, I want to see three neighbors, but it has all maybe 5 neighbors have the distance, same distance to the target. So you couldn't, it's not good to use this when you have all categorical feature. And actually decision tree is a better model if you have many categorical features. Okay, so that's what we will introduce at the next lesson. Okay, so we'll save the rest of the time for questions about the assignments or about the lessons, and on Thursday we'll talk about division tree.